All right, our first virtual lesson. Here we go. So before we get into more like circuit reducing, you read that article from Khan Academy, but if we, maybe didn't watch the video from Monday recently, or we're kind of just lost in all this, let's do a quick recap on what we know so far about series and parallel. Things that are in series, series circuits, or it doesn't have to be a whole circuit. It could just be elements that are in series. So I'm going to show you kind of a complex circuit and show you different parts that happen to be in series. So let's say that there's a circuit that looks like this. Something like that. Different parts of this are in series. So you have these three all in a row that would be considered to be series. But then once you get to this break, this branch, you can't just keep connecting that and claim that these are also in series to these three here. So in order to qualify for resistors to be in series, they have to all be in a single line that doesn't branch off one after another. So if we call this like R1, R2, and R3, they all come right after each other, and it's before that branch, and so we can call those in series. Well, then we'd have these two, which would be in series to each other. You'd have these other two that are in series to each other, but they're sending actually in parallel branches. You see on their each in their own kind of side-by-side parallel branch. That's why we draw them like that. The circuit kind of split here. So if you imagine current, let's say coming out of the battery this way, they'd be going across these, and they'd get to this point here, and some of the current would go this way, some of the current would go this way. But all of the current that goes this way has to go through these two, and that's why we say they're in series. And the current that goes this direction has to go through these two, and so those two are in series. Once both of those channels, let's try to do this together, they come back up and they combine together here, then you get that full amount of current. You get that full amount of current kind of rushing together all across those last three. So that's the properties that allow you to be in series. Oh, we left out one. So this group down here would also be in series to each other. So four unique series connections in this complex circuit. So let's go over to parallel. And in order for it to qualify as parallel, there has to be a split branch. And so we'll kind of draw a few different ideas here. So let's imagine a circuit that looks like this, and you got like 1, 2, 3, 4, and 5 different resistors in there. And the branches that are parallel, they are these connections here. So this line, and this line. Now in this last one, we actually have 2 different resistors in there that are in series to each other, but you'd say that this branch is parallel to this branch, which is parallel to this branch. So what is the idea of parallel? Well, basically, there's a wired connection from this side of the resistor. Let's call it the high potential side. There is a straight metal wire connection to all the other positive sides of those resistors. And so what that means is that they're all actually receiving the same potential at that location. So the idea behind parallel is that you'll have the same volt drop or potential difference down each branch. So if I compared, let's say this point here down to this point here, it would have the same voltage. If I tapped across those two leads, you'd get the same voltage as if you tapped here to here. or here to here. You can really think about though, all of those wires are just combined into one big, let me just redraw this. This would be like a circuit that just has one big joint here that splits into these three channels, and they all come back together into another spot here. And so this point to this point, if you tapped across that with a voltmeter, you'd get the same potential difference. And so it doesn't really matter which branch you're talking about, whether you're talking about this branch, or this branch, that corresponds with this, or this branch. You'd get the same voltage drop or potential difference. So my ski hill analogy, you're thinking for parallel, it'd be like if you were up at the top of a run, no matter which run you went down, 1, 2, or 3, you would drop the same amount of height by the time you got down there. You'd give up the same amount of energy by the time you got down the hill, and then you'd be at the bottom of the hill, no matter which branch you went down. So that's why parallel all has the same voltage down each branch. So let's apply those ideas of series and parallel to circuit reduction. There's kind of rules for how we treat equivalent resistances when they're in series to each other or whether they're in parallel to each other. So that, for instance, resistors 1 and 2 that are hooked up side by side like this, they're in series, they're really just acting like a resistor that has the total resistance of whatever R1 plus R2 is. That's the rule for series. If they're connected in series to each other, you can just add up the two resistances, and that section of the circuit is acting like a single resistor with just these two put together. The problem is then you have like these complex parts where there's like two parallel branches, and then you got things that are in series. So in circuit reduction, we kind of systematically work through this and reduce what we can so that we can talk about the final amount of resistance of this total circuit. So the first thing I want to identify is parts that are in series that I can kind of scrunch together. So I'm imagining R1 and R2, those are in series. R3 and R4 are in series. And so I could redraw the circuit, scrunching those together into a single idea or a single resistor, and I'll draw that next. So now that circuit will look just like one resistor up top here. We'll call that R1 plus R2. And that's going to go down to a single resistor here that we'll call R3 plus R4. And then goes to R6 and back to start. Then we got this parallel branch out here called R5. All right, so we've reduced all of the series connections that we can, and then the next step when you reduce circuits is to take care of your parallel branches. Now, the parallel branches have kind of this weird rule that, let me just write out the rule for parallel. For parallel equivalent resistance, equivalent, it's just really a fancy way of saying the total in parallel. The way you do that is the equivalent resistance will equal 1 divided by R1 plus 1 divided by R2 plus however many different branches or terms there are that are in parallel to each other. So you really identify your things that are in parallel, and we can only, these R1s and R2s kind of stand for one resistor at a time. So if there were any that were, let's go back over here to the first circuit. If there were any that were in series to each other beforehand, you got to combine those first before you're ready to do this last part of the equation. So I'm looking at this and I see these two parallel resistors, this one that we call R3 plus R4, and this one that we call R5. And so we could write out the math to that this whole section of the circuit is really just 1 divided by R3 plus R4 plus 1 divided by R5. That will equal this equivalent resistance. That's basically what this whole dotted line that I just drew is acting like would be equal to that formula there. So you have to do the denominator first. So that's kind of like in parentheses, that 1 over this term plus 1 over the other term. And then after that, you invert that whole that whole section. So now let's redraw this next circuit. And I haven't put any numbers to this on purpose, just to kind of start off with the theory, and then we'll do some numbers. All right, so we started with this circuit up here. We reduced it once. Now we're going to reduce this parallel section. And when we go to redraw that, then we have this thing called R1 plus R2. Then this whole parallel section is really acting like a single resistor whose amount of resistance is equivalent to all of this stuff up here. So I'm just going to reuse that and drag that down there. The total of that resistor would equal this math expression. When you have real numbers, you can actually like shorten these up and get like 6 ohms or 5 ohms. And so it's not as much like notation to keep track of. But when we're just doing strictly these variables, we have to leave all that in there. So that's how much that resistor would be. And then in our part of a circuit, then we're just going back to R6. So it's not like we've got rid of these chunks. If you go back, we've accounted for all that parallelness by representing it as one resistor of this amount. We've taken care of this series part by representing it as one resistor, R1 plus R2. Well, now you kind of see the last step of this, that this circuit here, let me just move this whole section over. That circuit here can be reduced one more time, and then really it's just acting like a single resistor if I just add up all 3 of these together, because now according to our series rules, you have 1, 2, 3 all in series, and you can just add them up. So my final idea is that I have a single voltage source with a equivalent resistance of R1 plus R2 quantity plus 1 divided by R3 plus R4 plus 1 over R5 quantity plus R6. That whole deal is really one single value of resistance. I got one single value of voltage here. And so you can just use Ohm's law now. V equals I times this big R down here. And you could solve for how much current comes out of the battery. This amount of I that would be shooting out. So what we do with that, this last picture you have to remember is kind of an analogy. And once we know how much total current would be coming out, we actually go back to our original circuit, and we'd say, now that I know the amount of I coming out, I can know how much is going across each of these devices, and then we can split it up and see how much it goes into each branch. So we kind of have to go back to our original when we go to solve other things, and we'll practice more of that with the real scenario next. All right, so example problem time. Consider the following circuit. You have a 9-volt battery here, and then you have all of these little resistors in your circuit. Some are in series to each other, some are in parallel, but the amount of ohms is listed next to each of them. That's 1 ohm, 4 ohms, 6 ohms, 2 ohms, 3 ohms, 4 ohms. Anyway, we're going to try to reduce that circuit. So the first step I would do is look for any series connections that you can join together and re-represent. So I'm identifying Looks like one here that I could add that 1 and 4 together to make 5 ohms along that branch. And 2 and 3 ohms here would add together, and that would reduce down to 5 ohms. I can't really add anything else in series to each other because there's not multiple resistors in a single line. So let's go ahead and redraw that once as is. So, okay, that's like a 9 volt that goes to a 2 ohm, that goes to a 5 ohm, that goes to another 5 ohm, then they all come back to a 6 ohm, and we have that shortcut. Now, I can't really reduce any more series, so I'm going to move on and try to do parallel. And it does look like I have now 3 parallel resistors to each other. So I can do the math of that's all acting like 1 over 5 plus 1 over 5 plus 1 over 4. And I got to look for common denominators. So let's see, 5 and 4, we could do 20. So I'd have 4 20ths plus 4 20ths plus 5 20ths, all inverted. And you got 8 plus 5. The total of that, we're going to have 13 20ths, but we flip it over. So that all of that section is acting like 20 over 13 ohms. So that's what that whole chunk acts like. All right, so almost done. So we got this 9 volt now that's going to a 2 ohm resistor. And now all of that chunk is going to act like a 20 over 13 ohms of resistance, which if you don't have a calculator is about 1.5, I'll try to be as precise, 1.538 ohms. We're going to have to round it. It's irrational. And that's something to kind of keep in mind. Usually the AP exam gives you really nice resistances that will come out to whole numbers, but for our example, I just made up some numbers. So we're almost done there. Then that goes back to a 6 ohm resistor and back to start. All right. So the last step is we could reduce this one more time because now I have three resistors that are all in series to each other. So I got 6 plus 2 is 8, and 8 plus this additional 20 over 13 gives me a final circuit that looks like this. 9 volt battery, one single resistor with a total of 9.538 ohms. So then the question is like, all right, well, what are you supposed to do once you reduce it all? Usually the whole point of reducing it is to get to the amount of current that's flowing out. Once you know the amount of current, then you can solve for different things in the circuit. Like they probably would have asked, like, what is the volt drop across each of these channels? Or what is the amount of current running through this section or this section? So you got to kind of know the total current before you can get any further. So if I know my total voltage and my total resistance, now I can get my total current coming out of the battery, which has to be the same amount of current coming back into the battery. Because remember, at any given point around the circuit, we have to have the same total current. So I'll just do that math. 9 divided by 9.538 gives you a current. So I just use Ohm's law there. V equals IR. So I equals V divided by R. And so if I take that 9 divided by 9.53, I get 0.9, we'll just go to the hundreds, 0.94 amps. So let me go all the way back to my first circuit here. Now that I know how much current's coming out, I know now that there's 0.94 amps coming out. And what that means is that there has to be 0.94 amps coming back in So you imagine, like, what else does that 0.94 amps flow across? Well, it flows across this right here. This gets 0.94 amps. It flows across the 6 ohm to come back to the battery, so that gets 0.94 amps. And this notation, I like to kind of draw it as an arrow across and label the value. That way, when I'm going back, I can say, all right, I have a resistance value and I got an amp value, so I can get to the voltage really quickly out of that. So voltage equals IR. So I could get the volt drop across each of these as if you were to tap across it with a voltmeter like I just drew. You could just plug in the numbers 2 times 0.94. And that gets you 1.88. So I know that the voltage here is 1.88 volts. And I could do the voltage here. This voltage would be 6 times 0.94, 5.64 volts. All right, so how is that helpful? Well, I have to drop a total of 9. By the time I get all the way around my circuit, imagine little skiers getting off the ski lift at 9. By the time they go down this ski run and get across this last hill, the 6 ohm hill, they have to get down to 0. So they're going to drop 1.88 just going across this. They're going to drop 5.64 just going across this. And so that only leaves so much that you can drop from here down to here, or from here down to here. And like we said in our original, in the first part of the video, how parallel works is that you're going to drop the same with no matter which branch you go down. So these parallel branches, they're all going to have the same volt drop, because by the time that you go down that branch, your only other option is to go across that 6 ohm to get back to start. So now we can just see what the voltage is across each of these. And I got my total. So V total is 9. Whoops, let me write it out with a pen. So I'm taking 9 volts from the battery minus 1.88 volt drop minus 5.64 volt drop. And that leaves me with a total of 1.48 volts that still need to be dropped. So that tells me from this point here down to this point here, I drop 1.48 volts. Same thing with these two. Same thing with this single one. Now that I have the voltage across each of those, and I have the total resistance, like there'd be 5 ohms in this line, 5 ohms in this line, 4 ohms in this line, I can do Ohm's law to solve for how that current gets split up in all 3 of these. So something that you just wouldn't be able to eyeball and like just know how much current and voltage is across each of these devices, you can do that with circuit reduction. And that process just involves first identifying all your series connections, then reducing your parallel connections, and then working your way around the circuit using Ohm's law to solve for different values. If you have questions, I'll be on Google Chat and possibly Google Meet to kind of give some one-on-one feedback as you get stuck.